Hello, welcome to a new group class. Today we're going to be looking at some anatomy and physiology, more specifically cardiac cycle, blood flow, cardiac output and stroke volume and the relationship between those three things. So it's going to be a good one, probably running for, I'm aiming for 45 minutes, but we'll see if we come under or over that, but that's the goal at least. So we're going to dive straight in. Before we do, there are some resource sheets and activity sheets that go with this. If you do want to find where they are, head over to either thepetutor.com or GCSE as well. If you're watching this in group classes or master classes through any other medium, then obviously you'll already have access to those resource sheets. So yeah, just listen out for when you need to go there. If not to worry, there are still plenty of activities and questions for you to be doing inside these slides and get as much out of this as possible. So we're going to get straight to it and looking at, well, the objectives for this session. I will move the presentation up in a bit just to make it a little bit bigger, but you'll see why in a moment. So yeah, first objective, to know what the route of the blood is. Okay, what route does the blood take around our body and, more importantly, through the heart? And by looking at this, we are going to be recapping different terminology used to label the heart, so the structure of the heart, as well as some of the major blood vessels that connect the heart with the pulmonary circuit and the systemic circuit as well. We should also know what the term dual action pump means and how this influences the cardiac cycle. And lastly, we will be looking at that relationship with stroke volume, cardiac output, heart rate, and what exercise and increasing exercise intensity might do to these levels. So there we go. If you want to pause the video, or if you're doing this in a lesson now, might be a great chance for a bit of a starter activity. I'm not going to pause the video now, but the option is there for you to do this if you want to. Right, make this a little bigger. There we go. So, cardiac blood flow. What is it? Well, you can see from this picture that we've got two different sides of a heart, and we need to remember, first of all, because there's going to be a lot of lefts and a lot of rights in this lesson, we always refer to anatomical position from our own perspective. So at the moment, yes, I am and you are looking at that heart, but we talk about it in respect to your own body. So your right-hand side is technically the left-hand side of that heart as you look at it. Okay, so if you are analysing someone else or an image or a video, even though it looks to be on your left-hand side, think of it from the perspective of whose heart or whose limb it is. So the one that's highlighted in that reddy orangey colour at the moment, that would be the right-hand side of the heart. And the first thing that we can see here is that we have these arrows coming into the heart and then back out of it. And because we're dealing with the right-hand side, any chamber that the blood is entering is also termed the right-hand side. So we've got this main blood vessel bringing this deoxygenated blood back in, this blue blood. Although it's not blue inside the body, we just use the colour blue to denote deoxygenated. Now this blood vessel is also called the vena cava. Now there are two different parts to the vena cava, you could say, the superior and the inferior, but your main piece of understanding will need to be that it's the vena cava. If you did need to refer to a particular part of it, then superior vena cava would be the one to go for. Now this vena cava brings deoxygenated blood back into the right atrium. Now the easiest way to remember atriums and ventricles, I have mentioned this before in a previous video, but if we look at the letter A and the letter V, think of them like arrows. So the atrium is pointing upwards and the ventricle, or the V, is pointing downwards. So atrium are in the top part of the heart, if that is a bog standard diagram of the heart. The atrium are in this top section, whereas the ventricles are in the bottom section. Just a quick tip for you to remember which one is atrium and which ones are ventricles. Okay, so we know that the vena cava is delivering this deoxygenated blood back to the right atrium, right-hand side, top of the heart, atrium, and blood is then forced through from atrial contraction, which we'll cover later on today. But it's forced through these valves, these atrioventricular valves, into the right ventricle. And then once the blood is inside the right ventricle and there's some more contraction, blood is then forced up and out of this right ventricle through the pulmonary artery. Pulmonary artery. Now, pulmonary, because this refers to the pulmonary circuit. Think about when we've spoken about respiratory system before. Pulmonary ventilation is the act of breathing in and out. So pulmonary refers to in the context of lungs. It's got things to do with lungs. So the pulmonary circuit is the circuit of vessels that connects heart, blood flow, and the lungs. The systemic circuit, which we'll cover later as well, is that's not necessarily below the heart, but it's the body. It's the bodily systems. So systemic circuit is from heart to body, whereas pulmonary circuit is heart to lungs. We will cover that again. So the pulmonary artery is delivering this blood from the right ventricle up into the lungs. Now, artery, because A for away, vein, V-E-I-N, I-N, in, is going back into the heart. So we know it's an artery because blood is moving in the direction away from the heart. So we've been up to the lungs. Okay, this blue line, this blue flow, this blue pulmonary artery is travelling up towards the lungs. This deoxygenated blood then picks up new oxygen and drops off CO2. In the process, it's becoming oxygenated. So we now have this red line which is coming back down from the lungs towards the heart. So we've got the pulmonary artery leaving, going away from the heart. It then arrives at the lungs, picks up oxygen, becomes oxygenated, and then comes back in to the heart. So we now have a vein. So the pulmonary artery goes up, the pulmonary vein brings this blood back down. And it's being delivered against the top part of the heart, which makes it an atrium, and it's on the left-hand side, therefore it's the left atrium, which we'll talk about in a second. So, there we have it. Oxygenated blood returning to the left atrium. It's coming into the top of the heart, A for the top ventricle, or V for the bottom. So it's coming into the top of the heart. It then passes down into the left ventricle, and when this left ventricle then contracts, it then goes up out of the aorta, okay, the aorta, and that's the vessel that then delivers it to the rest of the body. So oxygenated blood to the left atrium squeezes it down into the left ventricle. The left ventricle then squeezes the blood out of the heart into the blood vessel, the aorta, which is an artery, because the aorta is taking blood away from the heart. And the aorta is then delivering that rich oxygenated blood to the rest of the body. And in the context of sport, we care primarily about working muscles. So, to look at it all in one route, let's say, we'll start down at the bottom with working muscles. Okay, so the working muscles, we can see this transfer from red to blue. Oxygen is being extracted from the blood as this blood passes nearby working muscles. Oxygen is extracted, CO2 is deposited, and we've got this transfer of oxygenated blood into deoxygenated blood. Red to blue. So now this deoxygenated blood makes its way through the venous system, okay, through the capillaries first, then through the venules, then to the veins. The veins eventually converge into our two vena cava, superior and inferior, and the vena cava then plugs into this right atrium. Once the blood's in the right atrium, it's then forced down through contraction into the right ventricle. From the right ventricle, it is ejected away from the heart towards the lungs, A for away into the pulmonary circuit, therefore it's the pulmonary artery. And we've got this transition again of deoxygenated blood into rich oxygenated blood through gas exchange and diffusion. Two processes that we've looked at before in group classes. Then it comes back into the heart. Therefore it's a vein. We're still in the pulmonary circuit, therefore it must be the pulmonary vein. And it deposits it at the top of the heart, the atrium on the left-hand side. Therefore, it's the left atrium, which then contracts, ejects blood down into the ventricle, the left ventricle, which then contracts itself and ejects it away from the heart into our new blood vessel, an artery, the aorta. And then the process repeats. And we have this blood flowing around our body. We have this fresh supply of oxygenated blood to working muscles, delivery back to the heart, back to the lungs for oxygenation, back to the heart to then be pumped around the body once again. So, these are the sheets I was talking to you about. If you do have them, then now would be a good time to either pause the video and then complete this chart. If you are joining us live or you haven't got these sheets, then obviously just make a note of everything that we have been talking about, especially this cycle here. Okay, that there is a snapshot of all the key terminology to describe the main stations of blood flow around the body. So, moving on, we are now going to be looking at this phrase, dual action pump. Now, dual means two. Okay, so two of something. And in terms of the heart, there's a couple of different ways that we can describe the heart as having two of something. First of all, it pumps twice. If we think about a heartbeat, there's a thud, 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 thud. There's two separate beats, two separate contractions, two separate stages of a pump. So each pump represents one part of this dual action, the first half and the second half, top and bottom. Now the first thud you hear, if we think back to that cycle that we just had a look at of blood flow, it went atria, then ventricles, then pulmonary circuit. Atria, then ventricles, aorta. Now we've got the atria contracting, thud, 1. Then the ventricles contract, thud, 2. Thud, 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 thud. Now it's important to remember that both atria contract at the same time and both ventricles contract at the same time. And that's possible because we have two halves of the heart. We've got this septum that runs down the centre of our heart. It's a wall. And this wall prevents this blue and red blood, or in reality, the deoxygenated and the oxygenated blood from the right-hand side and the left-hand side. This septum, it stops the blood from mixing. So when both atria contract, boom, both volumes of blood flow down into their respective ventricles, but they don't mix. So we've almost got two stages of the pump, thud, thud, but we've also got two halves of the heart, one pumping blood up to the lungs and one pumping blood to the rest of the body simultaneously. Because when those ventricles contract, thud, the right-hand side, the blue side, the deoxygenated side, as that ventricle contracts, boom, blood is going to be going up to the lungs at the same time, because ventricles and atria, they contract together, both atria, both ventricles. Boom, when those ventricles contract, right-hand side goes to the lungs at the same time as the left-hand side blood, the red, oxygen-rich blood, that's being pumped out the aorta at the same time. So both ventricles contract, blood's ejected into both circuits, pulmonary and systemic, at the same time. And the septum is what allows us to do this wall in the middle. Which is what I was talking about here. We've got, in that second paragraph, we've got the system circuit, or the systemic circuit, if you were to add an IC onto that to make it the official phrase. But think of it like the rest of the systems. The system circuit, the pulmonary circuit, is the one that joins the heart to the lungs. So if you look at that picture on the right hand side there, we've got this, not the blue side and the red side as such, it's more the top half and the bottom half. They work at the same time. Atria, thud, blood moves down into the ventricles. Ventricles, thud, blood's ejected to the lungs and ejected to the rest of the body at the same time. So all of this together, even though the heart's only one organ, as it says there in the bottom paragraph, one organ, but we've got two sides, two separate stages of the pump, two separate circuits that we're supplying simultaneously. And that's where this name comes from. Dual action, dual meaning two. One pump, two actions, two halves, two sides, two systems, all working simultaneously together to supply blood to the lungs for oxygenation and the body for deoxygenation, essentially because we're supplying the living tissue with oxygen. So we now know the heart has two pumps and both are split into a top and bottom half. The atria above and the ventricle is below. Atria, think the upwards arrow of the A, and ventricle, the downward arrow of the V. Now each chamber, I've already spoken about contraction, but the opposite of contraction is relaxation. So contraction, relaxation. Well, the atria and the ventricles, when they thud, when they contract, that's them working. But all the rest of the time, when they're not actively contracting and applying pressure to the blood, they must be in the opposite state. They must be in the switched off state. It must be relaxed. And we have a phrase for this, or not a phrase, a name, I should say. When a chamber is contracting, or the muscle around the chamber is contracting, we call that systole, or systole, as you might have heard it. And when the chamber is relaxing, and it's entering this relaxed state, it's expanding and it's receiving blood, because when the atria contracts, thud, the ventricle is expanding and receiving blood in a relaxed state. Following the atria contraction, thud, it then returns to a relaxed state and it receives blood from the vena cava and the pulmonary vein. So systole or systole, when a chamber is contracting and ejecting blood. Whereas diastole or diastole, when a chamber is relaxing and it's receiving blood. Just like a light switch, on or off, this cardiac muscle is on or off, contracting or relaxing. Systole, diastole. So if we were to look at this now, almost in the centre of that cardiac, or that blood flow cycle that we looked at earlier. If we start up at the top, atria, diastole. Okay, atria, diastole, we're looking at this top one here, where the atria is relaxing and it's expanding and it's receiving blood from the vena cava, this blue blood deoxygenated, and it's also receiving blood from the pulmonary vein. Once the atria, both sides, remember dual action pump, once both of them have filled up, the atria then receives signals from the brain to contract. So both atria contract, entering systole. So they've filled in diastole, they then contract in systole, and they eject blood down into the waiting ventricles, which were currently in diastole phase because they were waiting and they were receiving blood. They were filling. And the atria have just contracted, they've squirted all of the blood down, and the ventricles have filled up in diastole phase. We're now here. So we've gone atria diastole, atria systole, ventricular diastole, they've now filled up. We're now at ventricular systole. Bang! They now contract. They eject their blood. pulmonary artery on the right hand side up towards the lungs, and the left hand side out of the ventricles into the aorta, the artery away from the heart to the rest of the working body. And once those ventricles have worked, the ventricles now enter their relaxation phase. Diastole, ventricular diastole. So we've just done thud thud, and while that second thud was being completed, that turns to relaxation at the same time that the atria are receiving the next load of blood. And this cardiac cycle continues. So, have a little read as we talk through it. Blood returns to the heart via the vena cava, pulmonary vein, and fills both atria, diastole. Both atria then contract and force blood through the valves and into the ventricles below them, atria systole, at which point the ventricles must have been in diastole phase, filling and receiving blood. Then the ventricles, they enter their systole phase, their contraction phase. Bang! Blood's ejected away from the heart through the two arteries, the pulmonary artery and the aorta, while simultaneously our atria, which are currently in diastole, they begin to receive a new batch of blood. So how does this look? Okay, we've seen the words. How does this look in terms of pictures? Well, the AV valves. Okay, the AV valves, these are open as the atria contract. And the AV valves are the ones that sit between the atria and the ventricles. Atrioventricular valves. So they're open. And the ventricles below them are relaxed. And here you can see the atria contracts and blood is squeezed through and down into the ventricles. At which point, the valves then close back up. The atria, they've just done their job. They've gone from a contracted state into a relaxed state. So now it's the ventricles' turn. And the ventricles are now contracting. They now enter ventricular systole. And the blood is being shot out up here into the pulmonary artery, which is about to go to the lungs, which are up here, and out of the aorta, which is the red one, which is about to come down and away. At which point the ventricles then relax once again, and the atria above, they begin to fill again. Atria relaxed, and they're filling up. And these valves, you can see almost, they're there almost as doors, as gateways, allowing this blood to flow through at certain times. So again, if you did have the activity sheets, now's a great chance. If not, then it will be this. This is the crux of the cardiac cycle, the descriptions of how different parts of this heart are contracting and moving blood around our body. So if I were you, I'd have those 5 circles and have them labelled with the systole and the diastole, and then a bit of a description at each stage as to what is happening. But you definitely need the definitions of systole and diastole. Okay, moving on, final part. We are now looking at cardiac output, also written as Q. So if you're looking for the shorthand term or the abbreviation cardiac output, I know it's weird, I don't know why it's not CO. There probably is a reason, I'm yet to look that up. But Q, cardiac output. HR, heart rate. SV, stroke volume. So what is heart rate? Right, it's the amount of times the heart completes. Well, now that we know what the cardiac cycle is, we don't just want to say beat, because we know it's got 2 beats, first of all, it's got 2 sides, it's got 2 pumps, we've got systole and diastole, we've got all of this movement of blood through it. So what we can now say is a heart rate is, well, each time, or how many times in 60 seconds, the heart completes a full cardiac cycle, a full contraction cycle. And we measure it per minute or per 60 seconds. And for an average person at rest, we're talking 70 to 80 beats. Now, we do have this phrase when we start to see an athlete or a highly trained performer drop below 60 beats per minute. That's actually got a name. It's called bradycardia. Bradycardia. So below 60 beats per minute, it's got the term bradycardia. B-R-A-D-Y cardia. C-A-R-D-I-A. Not essential to know that, but just an interesting fact. So, second of all, we've got stroke volumes. We know what heart rate is. Number of complete cycles per minute. Stroke volume. Well, this is how much blood is being moved during each individual cycle. So the amount of blood ejected from the left ventricle each cycle, each contraction. Remember, the left ventricle, this is on our red side. Okay, it's oxygenated and it's about to leave through the aorta to the rest of the working body. The amount of blood, the volume of blood that's leaving that ventricle, okay, not the amount of fill, okay, key difference, and we'll talk more about that in a moment, but the amount that actually leaves. So for example, if I've got a water bottle here, it's filled up, what's that, 2/3 of the way. Now if I took the lid off and just squeezed it, well, 2/3 of water isn't going to come out. So that isn't the stroke volume. What would come out, that is the stroke volume. So we've almost got this difference of pre-fill, we then eject it, and then we measure what's left over. The difference would be the stroke volume. We'll cover that in a little bit more detail, either later on or another time. So stroke volume is highest during moderate activity. There is a reason for that. Again, we will cover that. But it's key to know that we can't always increase stroke volume. It's this increase in combination of heart rate and stroke volume. That's what we need to achieve in order to increase cardiac output as a whole. Because if we're exercising, and we do have graphs for this, if we're exercising and intensity is getting harder and harder and harder, so if I put intensity here, and that's getting greater and greater, cardiac output, we want that to increase. Cardiac output is the main thing. So I'll quickly expand myself there. Cardiac output, this is what we want to increase. Now it doesn't really matter to us if our heart rate does a little bit of a dance, or our stroke volume does a little bit of a dance, but as long as the combination of these two leads to an overall increase in cardiac output, that's the main thing. So we can't expect for heart rate to increase linearly. We can't expect stroke volume to increase linearly. That's not how the heart functions. There's too many factors at play, with pressure change, with timings, with volume of blood returning to the heart or leaving the heart. Frequency of beats determines how much blood can actually fill up in the heart in that space of time. But as long as there is a relationship between the two that leads to cardiac output increasing linearly, that is the main goal. That is what our body and heart is trying to achieve. And what is the cardiac output? Probably should have said that first. Cardiac output is the total volume of blood ejected from the heart each minute. So applied to that graph, if exercise is getting harder and harder and harder, then we need more and more oxygen and more removal of CO2. Well, we want more blood to arrive at that working muscle. Therefore, we want more blood to be ejected from the heart each minute. And cardiac output, it's this result of the relationship between heart rate, frequency of cycles, and stroke volume, the amount ejected per cycle. So heart rate, just to recap, we know is the frequency of contractions. We know that each contraction creates pressure in the chambers of the heart, and we know that blood flowing through the heart is going to be squeezed more frequently. So if we start to combine those two factors, we know that more regular application of force is going to lead to a build-up of pressure. Things are going to move faster because they've got less time to slow down. Imagine if you had trying to think of an example, a revolving door perhaps, or maybe a desk chair. If in your classroom you've got, the teacher might have a swivel chair, well, if you push that chair around, it's going to speed up and then gradually decelerate. And if you pushed it every 3 rotations, it's got loads of time to slow down in between each one. The speed slows down. But if you were to apply a push every single time it rotates, you don't give it a chance to slow down. You're adding more force into that rotation. Well, similar sort of concept with our heart and blood flow and blood speed and blood pressure. The more frequently we contract, the more frequently we apply pressure to the blood, the less chance we give the blood that is moving to slow down. And this cumulative effect starts to occur. This build-up of force applied to the blood increases its speed. So we've now got blood travelling, looking at that last point there in the blue box. Blood is travelling around the body faster. And if it's doing that, it's going to get to the lungs quicker, pick up oxygen quicker, get to the muscle quicker, get rid of the CO2 quicker. And our body becomes more and more efficient at delivering oxygen, collecting carbon dioxide. So this is very similar to what I just showed you on the whiteboard behind me. But what you'll notice is that wiggly line isn't absolutely linear. It's not that predictable. The main reason for which is we've got all of these hormones running around our body. We've got all of the impulses from our brain trying to control and guess almost how hard our body's working. Chances are the intensity as well isn't going to be linear increase either. There'll be slight differences between how hard you're working from one 30-second period to the next 30-second period. If you were to go out on a 5k run and use, Strava or some sort of speed tracker, chances are you don't keep to the same pace. You might be able to keep it within a 5-second window, maybe lower if you're really, really good, but chances are there'll be a 10, 15, 20-second pace variation per kilometre that you complete. And that slight variation is going to be picked up by your brain, which is going to translate into a slight variation in your heart rate. The terrain might change. The wind might change. All of these external factors which determine the level of stress your body has experienced will translate into a non-linear heart rate increase. Yes, it's going from low to high, but the route it takes, it might be a little bit wobbly. Wobbly? So, stroke volume, we know, is the amount of blood ejected per beat. And we know that when we start to exercise, more blood is squeezed back to the heart by the working muscles. This concept of venous return. If I were to have blood sitting in blood vessels in my bicep, which, our veins, our venous system is effectively a reservoir. I think it's about 30 to 40% of our blood at any one time at rest is sitting in veins. It's almost queuing. It's queuing, waiting to get back to the heart to then get pumped around, and then it joins the back of the line in the veins. It slowly creeps back to then get pumped around to join the line again. So when we start to move, we're effectively speeding up this line, this queue. And one thing could be, as my muscle contracts, the vessels inside of it and around it, they're squished. And as they're squished and squeezed, the force inside, it applies a force to the blood that rests inside the vessel, just like a tube of toothpaste. If you leave it on the side, no toothpaste comes out if the lid's off. If you then press the tube of toothpaste, toothpaste comes out the end. Now it doesn't go out the back end of the toothpaste tube because that's all sealed up. And that's called pocket valves in the context of our blood vessels. Okay, pocket valves in our veins, they're almost like the door that closes. So blood's let through and then a door swings shut behind the blood. So that when there is pressure applied to that vein, such as a muscle contracting, the blood's squeezed, it can't go backwards, so it has to go forwards in the direction of the heart. And this extra blood coming back to our heart, well, that stretches our atria. If we think about atria diastole, they're filling up. Well, if we've got more blood returning to the atria, that's going to fill up and then stretch and stretch and stretch before its next contraction. And if that volume of blood, that increased volume of blood was in the atria, it's going to be passed to the right ventricle, it's going to be passed through the pulmonary artery to the lungs, down the pulmonary vein, into the left atrium, and then it's going to get passed down into the left ventricle. And we know that the stroke volume is the volume of blood ejected from the left ventricle. But it starts with this venous return. If we can stretch that first chamber, that right atrium, that stretch, that increases its volume, that goes to the lungs, that comes back to the left-hand side of the heart, that ends up in the left ventricle, which is then ejected again. But, and I'm looking here at this last bullet point, this is what I was talking about. We can't always increase stroke volume, because as that atria is in its resting state, its diastole phase, and it's expanding and it's receiving blood in, that's fantastic. That's great for our body, increasing stroke volume. But it takes time. It's only able to fill up to its maximum capacity because it's, if our heart's beating at 100 times a minute, it's got half a second almost. Half a second of filling up time before it contracts. Fill up for half a second, contract. Fill up for half a second, contract. But there will come a point where our heart rate, which is going up, starts to shrink and reduce the amount of time the atria has to expand and to fill up. So with less time to expand and fill, well, we're not going to reach the same volumes. And that's what this graph here in pink is. Stroke volume peaks at moderate intensity exercise, around that 100 beats per minute mark. Beyond that, with heart rate continuing, there's my mouse, with heart rate continuing to rise up here, we start to see stroke volume drop because there isn't enough time to pack maximum amounts of blood into that atria, pass it through so that it ends up in the left ventricle to then get ejected. But remember, as long as the relationship, I think that's on the next slide actually, as long as that relationship leads to cardiac output increasing, that's all that matters. So the cardiac output, the volume of blood ejected from the heart every minute, is determined by that combination of heart rate and stroke volume, two terms we've just looked at. And we need this increased cardiac output if exercise intensity is increasing. Okay, it won't keep on going up if we plateau in intensity. There might be there might be a little bit of a lag. So, if exercise intensity hits a plateau, so exercise intensity, how do we say it? So, if exercise intensity, if I go on this side, so intensity is in black. If intensity increases at the start of exercise, and we then, we get into a rhythm that we're jogging, and we run at that for 20 minutes, 30 minutes, and then we have a little bit of a sprint finish at the end, or we go up a hill at the end of our run, well, our cardiac output it isn't just going to increase indefinitely. It's going to match, it's going to plateau. So it's going to increase at the start, probably a little bit behind. It will then plateau itself, and then it will increase towards the end. So we've always got this bit of a time lag between plateau in intensity and then the plateau in cardiac output. Now, what controls this cardiac output? That's what we've just been talking about. Heart rate, stroke volume. And heart rate and stroke volume, they can chop and change, increase, decrease. But as long as the relationship between the two leads to a cardiac output that satisfies the current energy demands of the exercise intensity, that's what we care about. Is there enough oxygen being delivered? Is there enough CO2 being extracted? Is the lactic acid being broken down at a sufficient rate that it doesn't cause our muscles to get tired? So as long as intensity is increasing, so too will cardiac output. If intensity plateaus after a little bit of a time lag and changes to heart rate and stroke volume, cardiac output will also start to plateau. But one of the last things I want to talk about today is anticipatory rise. Now, that word there, anticipatory, you're probably thinking sounds like anticipation. You're right. Anticipatory rise is this spike, sharp increase in heart rate in anticipation of starting. So heart rate, stroke volume, cardiac output, they don't wait for the exercise intensity to increase. Well, I say that, but this is so long as you know that exercise is coming. You know, if you were just sitting down, let's say right now you're not expecting to have to do any exercise, but let's just say I said do 10 star jumps, you would do 10 star jumps, there wouldn't be any anticipatory rise because you didn't know that it was coming. But if you plan to perform exercise, let's say you're a netball player and you're out on court, you're marking your player, and you know that the whistle to go or to start is about to blow in a minute's time. That's when anticipatory rise might kick in. This anticipation, this foresight of you thinking about exercise, it can release a little bit of adrenaline. That third point. Adrenaline is a hormone. It's secreted by adrenal glands, controlled by our hormone regulatory systems. You don't need to know that in any detail for your exam, except adrenaline causes your heart to beat faster. So when you're thinking about impending exercise, I should say, adrenaline will start to be dripped into your body. And that's going to have the effect of increasing your heart rate. And if we're increasing our heart rate, think about the relationship. Heart rate times stroke volume equals cardiac output. So if we increase heart rate, stroke volume stays the same, we're still going to see an increase in cardiac output. So there it is. That dotted line. Before that dotted line, okay, pre-line, that's you at rest. But we see that blue line increase. Why? Because adrenaline has been dripped into your system. Heart rate has increased as a result. Then we go past the line, exercise starts. So we've got a head start. We haven't got as far to increase until our cardiac output is matching our exercise intensity. So that increase in heart rate and therefore cardiac output, that increase prior to exercise starting, that's called anticipatory rise. So these are the four graphs that we've looked at. We've got a heart rate, so the blue wiggly line. We've got stroke volume, which is the pink one that then drops off. The relationship between the blue and the pink one, that is what leads to the Q increase, gradual Q increase, all the while exercise intensity is going up. If that were to plateau, then so too would cardiac output. And then we've got the fourth one here, anticipatory rise, that red zone, that spike in heart rate, that sharp increase prior to exercise commencing. Why? Because you're thinking about it. You're anticipating it. Impending movement is drawing closer, the nerves are building, and your body releases hormones, adrenaline. The benefit? Well, we're halfway to increasing or meeting energy demands with our cardiac output. So I'll leave that on the screen. That there summarises what we've just been talking about in the last 10 minutes. The two lines, start of exercise, end of exercise. You can see there's time lag. The two or the three zones, I should say, that green box, anticipatory rise. That yellow box, stroke volume. That will start to drop off, all the while intensity carries on increasing. If exercise intensity plateaus, heart rate, stroke volume, cardiac output, they'll all plateau at the level that they currently meet, or met, I should say. And then at the end, once we go into rest, we don't just immediately drop down back to our resting levels. We have this gradual decline as the brain works out that we're no longer exercising, but there's still some recovery required. And there is an activity sheet for that. So if you have it, fantastic, download it, print it, complete it, store it, revise it. If not, then obviously you can watch this as many times as you need to, and you can go back to and pause on demand the different slides and information that you can recover to revise. And that brings us to the end. So hopefully you can list the route that the blood takes through the heart, describing the different structures that it passes through. We should know what the terms systole and diastole mean, contraction, relaxation, and then apply that to cardiac cycle. When the atria contract, when the ventricles contract, what impact does that have on blood flow? And then finally, we should now know what the terms heart rate, stroke volume, cardiac output, and anticipatory rise all mean, and how each of them respond to exercise intensity, and how they might relate to one another. Which brings us to the end. I hope you found that useful and enjoyed it as much as you could. Remember, if you are looking for similar things to this, be it GCSE, LCPE, A-level, IB, head over to thepetutor.com, where we've got one-to-ones, group classes, resource shop, YouTube channel, and our various portals as well, with everything from PowerPoints, worksheets, tutorials, frameworks, guidance, tip sheets, flashcards, everything you might need to study or teach PE. Head on over to thepetutor.com, and it'd be great to work with you and help you out any way we can. I've been Johnny, this has been Group Classes, and I hope to see you again next time. Bye for now.